Hi students. So today we'll start lecture 32 in our aerospace engineering course. I'm going to discuss about power required and available power, and we are going to cover propeller type of aircraft as well as jet aircraft. So this is a very important lecture, so stay tuned till the end of the video. I'm Dr. Ranjan Ganguly. Now let us just recapitulate some of the things we know about power. So we know that power is the time derivative of work, that is power equals dw by dt. Now we can write work as F into x, where x is the displacement in the direction of the force F, and if we then assume that force is equal to a constant, then we can bring force out of this bracket here, and we can write this as F into dx by dt, or F into v. So do recall from physics that velocity is the rate of change of displacement. So essentially this is the relationship between power, work, force and velocity. And of course, if you remember from physics, you would know that the unit of power is watts, the unit of work is joules, and the unit of force is Newton. So now let us turn the things we know about power and work into an airplane problem. So again, let's go back to our previous lecture where we looked at a typical airplane in flight, and this was essentially level unaccelerated flight. And so we found out that in such a condition the lift should equal the weight and the thrust should equal the drag. So let's consider a situation when the altitude is fixed, so essentially density gets fixed, and also velocity is fixed, so v infinity gets fixed. So in that kind of condition we can write the equations of motion for the airplane as thrust equal to drag is q infinity scd, and lift equal to weight is equal to q infinity scl. Now if I divide these two equations, I get thrust by weight equals cd by cl, and so I can write the thrust required equation as w by cl by cd, or w by l by d. So essentially what this tells me is that if I want to have minimum thrust, then I should fly in the situation of maximum cl by cd, which we discussed in our previous lecture. Now to get the equation for power, I can use the fact that power equals to thrust into velocity. So I can write PR equals TR into V infinity, and therefore I immediately get PR is W by CLCD into V infinity. So essentially all I have done is I have taken TR from this equation here, which is given in this yellow box, and I have put it into the power required equation and obtained this equation for power required. Now we are going to take this equation and develop further relations, but before that we are going to take a qualitative look at power required. So again, let's start with this value for power required, and then what we do is we take the equation for lift. So remember, lift equals weight is q infinity scl equals half rho v infinity square scl. So again, rho infinity is the density of air, v infinity is the speed of the body, s is the area of the wing, and cl is the lift coefficient. So from this particular definition, I can write v infinity as root of 2w by rho infinity scl. So it's simply coming out from this equation here, and we are using the fact that lift equal to weight in steady level flight. Now this v infinity we substitute back into the PR equation, and this gives us PR is w by CL by CD into root of 2w by rho infinity SCL. So let's take a look at this equation and then try to further express it in a simpler form. So what we do is we bring in the w inside the square root here, so that becomes w squared term, so it becomes w into w squared, that's a w cube term. We bring in the CL by CD inside also, so the CD goes and becomes CD square, and the CL becomes CL cube here. So when we look at this equation carefully, we see that power required is proportional to CL, or rather proportional to 1 by CL3 by 2 by CD. So this is something which is very interesting. The thrust required was proportional to 1 by CL by CD, but power required is proportional to 1 by CL3 by 2 by CD. So what this means is that if I were to plot power required versus velocity, I would obtain a certain minimum point, and that minimum velocity point where power required is minimum would correspond to the condition where CL3 by 2 by CD is a maximum. So that's something we are getting qualitatively from the equation I discussed before. So essentially what this means is that you should fly the airplane at an alpha where CL3 by 2 by CD is a maximum. Now what this would mean in practice is if the airplane is flying like this, remember the velocity is coming in this flight path direction, there is a small angle alpha between the flight path and the chord line, and these are the four forces which are acting on the airplane. Then you should fly this airplane at an alpha where CL3 by 2 by CD is a maximum. So this is going to give us the minimum power required situation. Now this was a very qualitative look at this power required problem. So next what we'll do is we are going to take a quantitative look based on equation. So we see that power required is a sum of the zero lift power required and the lift induced power required, and this comes from the fact that I can write PR is TR into V infinity, which means this is drag into V infinity. So recall that thrust equals to drag in steady level flight, and so I can then bring in the expression for drag from the drag polar. So essentially the drag polar equation comes here, and before that I put Q infinity S, the dynamic pressure and the area of the wing, and V infinity goes here. So the drag polar of course has two parts, the zero lift power part which is given by CD0, and the lift induced power part which is given by the CL square by pi EAR term, where E is the span efficiency factor and AR is the aspect ratio of the wing. So I can write this equation out if I expand it. So I get PR is Q infinity S CD0 into V infinity. This is one term. This is the term involving zero lift power, and the second term is Q infinity S CL square by pi EAR into V infinity, and this is the term which involves the lift induced power required. Now this equation has to be further manipulated so that we can express it in terms of weight. So essentially we use the fact that lift equals weight, and this is equal to half rho infinity V infinity square S into CL, and from here I can get the expression for CL as weight divided by half rho infinity S V infinity square, and then I put this expression for CL into the power required equation. So then I get this equation here, that power required is this part dependent on CD 0, and then there is one more part here. So this is the complete equation as far as the power required is concerned, and one more thing we have done here is that we have expressed Q infinity as half rho infinity V infinity square. So that's how the V infinity cube term has come here, and here also Q infinity has been expressed in that form, so the V infinity cube term has come, and this term here W by half rho infinity SV infinity square, it's simply the value of CL being substituted into this equation. Now we are going to spend some time in simplifying this equation and expressing it in a form where we can express these terms as CD naught or CD0 and CDI, which is the induced drag term. So to do that, let's take that equation I previously showed in the slide before, and then I rewrite it here. So essentially the second term on the right hand side is rewritten here. So you get the W square term here. You get some cancellations here for the rho infinity S V infinity terms. And so you get here pi EAR, and then you get half rho infinity S V infinity. So do recall that there is a square here. So here you would have a rho infinity square, S square, V infinity 4. And so after cancellations, you will end up with this kind of equation here. So now we take this power required equation here. We write it in this form here. So all I have done is I have taken this half rho infinity s v infinity and written it like this. And then what we do is that we take certain terms out. So actually here what I am doing is I'm taking the power required and I'm trying to find the stationary point. So essentially this involves differentiating P of R. So essentially I've taken dPr by dV infinity. So that has given me 3 by 2 rho infinity SCD0 V infinity square. So remember that V infinity cube would be simply 3 V infinity square if we were to differentiate that term. And here we would have a V infinity term, 1 by V infinity term, which if we differentiate would become minus 1 by V infinity squared term. So that's what has happened here and you have got this term. So this is essentially the derivative term. And why we are taking the derivative is because we want to find the minimum point or the stationary point of this function PR, and we have expressed this PR as a function of various constant terms. For example, rho infinity SCD0, WEAR, and also the velocity term. So we can actually find the velocity at which this function is going to be a minimum value. So we take the derivative here, we further simplify the derivative here by taking out 3 by 2 rho infinity V infinity square S, and so we get this equation here. Now we continue doing this process of algebra a little more, and so we get this term here, and we essentially need to realize that whatever you have on this numerator part of this term, which is involving W, is actually something we can represent in terms of CL. So if you go back and look at CL, that's W by half rho infinity S V infinity square, and I put it in this equation here, I can write this top as 1/3 CL square, and then I immediately realize that this term is related to CDI. So CDI is CL square by pi EAR, and then when I write it out I get this term here which I can then equate to 0. So do remember that if a function has a minimum value, then its derivative with respect to that particular variable V infinity here should be 0. So we can set this equal to 0, and so immediately I will get CD0 equals 1/3 CDI as the condition. So the stationary point of the power equation corresponds to CD0 equals 1/3 CDI, and this is the necessary condition for the minimum point. And if we want to express this in words, it simply says that zero lift drag equal to 1/3 of drag due to lift. So now we can actually take a look at the second derivative also, because if we are going to be proper about it, then any function which is differentiated and set equal to 0, that yields the stationary point. We don't know if it's a minimum, maximum, or a saddle point. So here I have taken the next derivative here. So we rewrite this dpr by dv infinity. We take the next derivative. So what happens is that the v infinity squared term simply becomes 2 into v infinity. So I get that 2 cancelled here. I get this term here. And here you have a term involving 1 by v infinity square, or v infinity to the power minus 2. So that term when differentiated will become minus 2 v infinity to the power minus 3, and so the minus sign becomes plus here and I get this equation. So now if you look at this expression very carefully, the second derivative of PR, you will see that all these values which are there are essentially positive values. So for example, they are all physical values such as density, the area of the wing, the drag coefficient, the velocity, the weight, the value of E, the value of aspect ratio, and so on. So this number is always going to be a positive value, and therefore we have in fact got the minimum point, because that's the sufficient condition for a function having a minimum point. So now let's go back to the equation for power required and plot it. And so if we do that, we can get this red curve here. So this is essentially the power required curve, and we can see this as two parts. That is a part which goes up as V infinity cube. So that's the zero lift power. and so that is the power which is going up rather dramatically here because it's a function of v infinity cube. So at higher velocities this will go up faster. The second term, which is the lift induced power, is inversely proportional to v infinity. So as v infinity goes up, this blue line goes down here. This is the lift induced power. So if I combine both these, I get this value here, and you will note that the velocity corresponding to minimum power required, that actually happens when CD0 is one third of CDI. So essentially the green line will be at some location which is much lower than the blue line here. So this is at about one third location here. So let's rewrite this equation for power required because it's going to tell us a lot about what we can do to control power required or to optimize on power required. So we see here that there is the red part which is totally dependent on CD0. That is the part which is all coming from the drag, and then this is the part which is actually lift related in the green. So if we look at this equation, we'll see that PR depends on aircraft design and flight condition. So for example, the flight condition variables would be air density and air velocity, that is rho infinity and v infinity, and the parts from airplane design would be the area of the wing, the airplane drag coefficient CD0, the airplane weight W, the Oswald span efficiency factor E, and the aspect ratio AR. So now let us look at the available power, and this will help us calculate the maximum velocity. So if we look at the available power, it will depend on the type of engine we are using. So let's first consider, for example, a combination of a reciprocating engine and a propeller, for example, in a typical aircraft such as this here. So these kind of engines are essentially driven by something which are coming from piston engines. So what happens in a piston engine is that you burn fuel in cylinders and the energy generated is used to move pistons which deliver power to a rotating crankshaft. So I've shown that here, and so what happens is that this rotating crankshaft is going to finally rotate the propeller. Now the available power PA is equal to eta into P, where eta is some number less than 1 is the efficiency of the propeller, and typically the rating of piston engines or in fact propeller based aircraft, often you deal with horsepower. So do remember that 1 horsepower equals 746 watts. So the curve which we often get for the available power in terms of velocity is given by this blue line here. So this is typically rated in terms of horsepower, and so there is a increase in this power as the velocity goes up. So this is very typical for the propeller type of aircraft. So if we are going to look at the maximum velocity for this propeller aircraft, the red line here is the power required, which we have seen before. The available power is from the blue line, and so where these two lines intersect, that's the point of the maximum velocity Vmax for the propeller aircraft. Now if we look at a jet engine situation, here the power is calculated from the available thrust. So for example, the available power PA is TA into V infinity, and if you recall, the TA value for a jet was almost constant, for example in our last lecture. Then if we were to multiply it by V infinity, we would essentially get something like a straight line, because at V infinity is 0, the available power would be 0 here. So if we look at a typical jet engine, the straight line, which is the available power, would intersect with the power required curve at 2 points, and the point here, which is in the high speed region, that would correspond to Vmax. So that's something to keep in mind. Of course, in the lower speed region, this is one possibility here. Now do remember, if you are in this region which is beyond the available power, then you're not going to be able to fly here. But also do remember that the stall speed is going to play a role in determining what is your minimum speed as far as the jet aircraft is concerned. So to summarize today's lecture, we saw that the power required curves are important for what is often known as aircraft performance or performance analysis, and the equation is given like this here. So there is a part due to CD0 which is proportional to V infinity cube, and the second part is proportional to 1 by V infinity. So this is the total power required curve. So it is an interplay on the part which is driven by the CD0 term and the part which is coming from the induced drag type of term. So also from differentiation and from the mathematics, we saw that this function which I showed in the previous slide has a minimum point at CD0 equals 1/3 CDI, and this is where you want to fly if you want the minimum power required condition. Also, propeller aircraft are rated in terms of power, jet aircraft are rated in terms of thrust, and the maximum velocity can be calculated from the point where the power required curve and the power available curve will intersect for either the jet aircraft or the propeller aircraft. So this was today's lecture where we talked about the power required and available curve. These curves are very important for airplane performance design. So as far as aerospace engineers are concerned, they do spend a lot of time in getting these curves, and then they can use these curves to do various calculations. But do remember that different curves are going to be obtained for different altitudes here. So what I have shown here is corresponding to a given height at which the airplane is flying. So for example, if you do this calculation at standard sea level, you are going to get a certain power required curve, and if you do this calculation at different heights, then that density is going to be different, so your power required curve is going to change, and that's something we are going to discuss in our next lecture. So I'll see you in the next lecture. See you then.